And thanks to the organizers for organizing this wonderful get-together, semester and conference both. So I want to try to, I'm interested in discussing sort of some of the aspects of the foundations of the theory of equivariant homotopy theory. So this is going to be sort of a foundational talk. And my interest is going to be in trying to share with you some of the story of the infinity categorical foundations and how that stuff was developed. But this is going to be an elementary talk in that sense. So I'm not really going to assume that you know, infinity categories inside and out. It would be good if you'd heard of the word and sort of vaguely know what kinds of objects they are. But I don't expect you to be hyper knowledgeable about it. And yeah, and there are really two questions that you want to answer if you're going to give a talk like this, I guess. And the two questions are how and why. Or maybe they should come in the other order. Why, in the sense of why would you ever go to all the trouble of setting up an infinity categorical foundations for something? I mean, there were foundations that already existed. They were good. They had nice properties. There were theorems. You don't need to do all this. And then the sort of how question is, what are the technologies involved? What kinds of higher categories appear? How do you use them? How do you make sense of them? What do you actually do to do this sort of work? And so I want to try to answer both of those as best I can. And I guess where I want to start is I want to start with unstable homotopy theory. And I want to start with, maybe this is part one. And I want to start with a comment that Clover made in her first lecture, which was that in equivariant homotopy theory, this is my abbreviation for homotopy theory, the points are orbits. And here for now, and probably for most of the lecture, G is just going to be a finite group. I'm happy to talk about what happens if G isn't finite anymore. But as long as G is finite, the stuff I'm saying will certainly apply. So the points are the orbits. That's the idea. Okay, so how are we going to use this idea to say something non-trivial about the unstable category of spaces, the category of G spaces? Well, and the idea goes back to the question of spaces themselves without equivariance. What kind of object is that? Well, if I think about it, spaces is supposed to form an infinity category. I'll just write space for that infinity category. And the theorem about this infinity category of spaces is that that space is freely generated under colimits. By what? Well, by a single object, which is the one-point space. So, okay, what does that mean? What does it mean to say that it's freely generated under colimits by the point? Well, one thing that you could mean by this is just that, well, every space can be written as a colimit of points. That's something that you already know if you've ever thought about CW complexes. Every space is sort of a weak homotopy equivalent to a CW complex. But here I'm saying something that's a little bit stronger. I'm saying that if you have, so if D is an infinity category with all colimits, and I take a functor from spaces to D that has the property, this is what this L is going to mean here, that has the property that it preserves all colimits, then specifying this functor here will be uniquely specified by what you do on the point. In other words, if I look at evaluation on the one-point space, that's a functor to D, this functor is an equivalence. And so it's in that sense that the infinity category of spaces is freely generated under colimits by the one-point space. All right, and now remembering that, I want to take Clover's dictum very seriously. And I want to say, well, okay, let's consider the orbit category of G. I never know whether the G should go up or down with the orbit category.
Yes. I mean, whatever.
If I put it in the middle, no one can be mad. I enjoyed how like fighty that felt. That was exciting. Let's see if we can get some more of that energy. Okay, so what does it mean here? So, well, if these things are going to be the points, then that means they must form a full subcategory of the category of G spaces. Okay, now where should the G go? G equivariant.
I would put it in front.
You put it in front? Like that?
I wouldn't even put a hyphen.
You wouldn't even put a hyphen. All right, let's not. Let's.
I would do that.
Yeah, but now I'm going to do it. I like it. It's fun. Okay, so what do I want here? I'm going to have a full subcategory like this, and these are supposed to be my new points, right? Orbits are the new points. So if orbits are the new points, then what does that mean? That means that if I have a colimit preserving functor from here to something, some sort of test category that I'm working with that has all colimits, then it will be determined, and also will obviously determine, a functor like this. So to say it again in this sort of language here, colimit preserving functors from G spaces to D, when you restrict to G orbits, that gives you a functor from G orbits to D, and this should be an equivalence. Or to say the same thing all over again, what we learned is that the infinity category of G spaces is, and I'm being really lousy about whether I write space or spaces, but that probably doesn't matter, is really just the functor category from the category of orbits to the category of spaces. Up, 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 up. It's the pre-sheaf category. And so this, you can either think of this as a definition or a theorem, depending on where you like to start this story. If you think of it as a theorem, then this often gets called Elmendorf's theorem, which Mike Hill referred to in his lecture yesterday. And the idea here is, well, if I want to tell you what a space is, then I'm just going to tell you what the diagram of fixed points are for all the subgroups of my group are, and that's going to be the same thing as the information of a G space. So that's what a G space is. So let me sort of mention something in the Y column here. I'm not going to actually make notes here, but in the Y column here, one of the things that this is doing is it's showing you that when you want to think about infinity categories, one way to use infinity categories in homotopy theory is to sort of take your favorite objects and put them together into an infinity category and study that infinity category, and that's a good thing to do. But the real power, the real conceptual power of infinity category theory comes by moving that story a level up. Instead of looking at your objects, lumping them into a category and then studying that category, the better thing to do is to think about the properties that that category satisfies and try to write down the universal property of that infinity category. And that's something that infinity category theory is uniquely qualified to be able to do. You can't tell that kind of story with, n categories for finite n. Okay, so this is, if you like, the universal property of unstable equivariant homotopy theory. Now, if you're a certain kind of brain, then when you look at the category of G orbits here, or maybe I really mean G orbits op, you notice that this category is actually kind of special. It's kind of special in various ways. I mean, when you think about the category of G orbits, Well, what can you do? Well, you can kind of map down to a poset. And that poset is going to be the poset of conjugacy classes of subgroups of your group. And now I need to choose an op convention here, so I think I'm going to do it this way, which is going to annoy you, but only for a short period of time. Okay? It won't annoy you forever, but it's going to annoy you for a minute. This is the poset of conjugacy classes of subgroups of G. But it's more than just that it's got a functor to a poset. Lots of categories have functors to posets. But this particular functor, this poset, has the extra property that it's conservative. Conservative in what sense? Conservative in the sense that a map becomes an isomorphism if and only if it already was an isomorphism. Isomorphisms in PG aren't that exciting, but there you go.
You haven't told us what PG is.
Well, it's this thing. It's this poset of conjugacy classes of subgroups.
All isomorphisms have been made the identity.
Yeah, that's right. All isomorphisms have been made the identity here. Right? And the order relation is subconjugate. Subconjugate. That's better. So what does that mean? That means that if you look at the fibers of this functor here, the fibers are all complexes. They're all infinity groupoids. They all have invertible one-morphisms and only invertible one-morphisms. Right? So when I think about the fibers of this thing, I want to think about them as homotopy types. But then this poset structure here is telling me I'm going to glue those homotopy types together in some fashion. And so you can ask, well, what is that fashion? How are you doing this? Well, just to give an idea here, let's think about the particular case of G equals CP, which is an example that we've thought about a lot this week. And I don't see any reason to stop now. So when I think about G equals CP, well, I'm going to look at the category of CP orbits op. So let's see here. So I've got CP mod E, and that maps in the orbit category to CP mod CP. So the map actually now goes this way because I'm looking at the opposite category. That's life. And then I've got CP acting over here. This is just the same diagram that Mike Hill wrote on the board yesterday. And, well, what's the poset that this thing maps to? Well, it's this rather thrilling poset right here. So if you have a particular frame of mind about these kinds of categories, then you might be inclined to think of this thing as a stratified space. And I recommend it. So here's how that story goes.
You want to use the ordering of superconjugacy instead of subconjugacy?
Yeah, because I've turned my arrows around. Yes, thank you. Superconjugacy is what I should have said. Thank you. Yeah. So here's the definition. A P stratified space. Maybe P here is going to be a finite poset. A P stratified space is an infinity category. Maybe I'll call it X, along with a conservative functor X to P. So for every element of my poset, I have XP, which is now a concomplex, so I'm just going to think about that as a homotopy type. That sits inside here. And then, well, what happens as you move from one stratum to another? This is called the stratum, by the way. This is the Pth stratum. As you move from one stratum to another, you have paths that exit that stratum. Now, they've gone really weird with the naming conventions, and they call these exit paths. So if I have p less than or equal to q, I can talk about exit paths starting in the pth stratum and landing in the qth stratum. And the idea here is that when we think about this, we're supposed to think about the p's that are smaller as being more closed than the p's that are bigger. This is the same direction, by the way, as the Alexandrov topology that we might use on this poset, in which the closed subsets are exactly the downwardly closed subsets. So just to illustrate, if we look at this rather unremarkable poset here, then this is closed and this is open. And so exit paths go from being in closed strata out to the open strata. They seem to flow in that direction. They exit. If you have a topological space, so if X is now, maybe I better not call it X, I'll call it Y. If Y is now a topological space, then you can stratify that topological space by writing down a continuous map to this poset. I won't give it a name, but there it is. And this is what might normally be called a stratified topological space. This is a stratification of this topological space Y. And when you have that, you can perform a construction, which is the formation of the exit path category. How does it work? Well, the exit paths are going to be paths. I'll just draw a little illustration here with the aid of this piece of chalk right here. So here, this yellow bit here is a closed stratum, or at least a more closed stratum, so it's lower in the poset. And this is a more open stratum, so it's higher in the poset. And then an exit path has to start in a stratum and go directly into the stratum that it lands in. Wherever it terminates, it has to go straight into that stratum. And that's what an exit path is. And as long as your topological space plus continuous map are reasonably nice, then when you construct this thing is now an infinity category. And furthermore, this functor here is conservative. So it's one of these. It's one of these stratified spaces in the abstract. I could have called these abstract stratified spaces, but these are the kind that I want anyway. So these are just representations of this as far as I'm concerned. So this is an infinity category. This space of exit paths, as I move from stratum to stratum, you can compose these once you guarantee that the topological space is nice enough. So that means that you've actually got an infinity category on your hands. And it has a conservative functor down to this poset. And so it's an example of one of these stratified spaces. I want you to think about this as a generalization of the way in which we build the singular simplicial set, or the infinity groupoid, if you like that sort of language, or the complex related to a topological space. Right? This is exactly the same construction in the case where P is a point, but when P is something more interesting, then you get this infinity category. It's not an infinity groupoid. Its fibers are infinity groupoids, however, because of this conservativity. The fibers are the homotopy types of the strata of your topological space, of your stratified topological space. And then you have linking information that tells you how to glue one stratum to the next, and so on. So when you're wandering in the desert and you encounter a infinity category in which there aren't any endomorphisms that aren't isomorphisms, then perhaps one of the thoughts that you will have is that, hey, maybe I should be thinking about that as a stratified space. Maybe I should be thinking about that with a sort of geometric picture in mind. And then I can reflect on the meaning of that picture as I do whatever I do with that infinity category. That is our situation over here. Right? We have an infinity category along with a conservative functor to a poset. So that tells me that I'm supposed to think about this thing as a stratified space. Okay, well, what stratified space is it? Well, I can see what the two strata are. This stratum is totally unexciting. It's just a point. And this stratum is rather more exciting. It's the classifying space of CP. When I put these two things together, what do I have? Well, I don't know how to draw CP. What I have is I have the cone on BCP. So when you think about the orbit category of CP, or rather its opposite perhaps, I want you to think about that as the cone on BCP. Notice that this ties in with what Jeremy Hahn was saying on the first day when he pointed out that, well, if you just think about spectra over BCP, that is to say, when you just think about spectra with the CP action and no further information, then that's not a very compact thing. Somehow the passage from these, well, I don't know if we're calling them naive or ersatz or what we're calling them right now, these non-genuine CP spectra, the passage from these non-genuine CP spectra to these genuine CP spectra is a passage to some sort of compactification. He also said another thing. He said that, well, when you're doing this, you were thinking about, on this bit here, on this open stratum, you were thinking about local systems. You're thinking of locally constant sheaves. And then when you passed to this compactification, you started thinking about constructible sheaves. And that's really true. So let me explain why that's really true. Is everybody okay? Are there questions? I feel like I'm talking too fast. How's everybody feeling? It's late in the day. Okay. All right. You tell me if you had questions, right? Right. So let's remind ourselves of the very worst way to teach a beginning algebraic topology student about the homotopy type. Here it is. So suppose that I have a manifold M, and I want to define its homotopy type. But I'm going to do so in the most obnoxious way I possibly can. So here's what I'm going to do. I'm going to consider for every infinity category C, yeah, see, it's already there. For every infinity category C, I'm going to associate to that infinity category the category of locally constant sheaves on M with values in C. That's a functor, right? And then, well, what about that functor? That functor is co-representable. No, really, this is not a good way to teach. That functor is co-representable, by which I mean that this is equivalent to the category of functors from something into C, C, and that something turns out to be an infinity groupoid, pi infinity of M. That's my preferred notation. I could have also written sing if you felt like that was nicer. So this is the representing object for locally constant sheaves. It doesn't really matter that M is a manifold, locally contractible, and such will do fine. It's not a big deal. Okay, so if that's true, then what about this exit path category? That's supposed to be a generalization of this thing. What is that generalization? What's the nature of it? And well, the idea is that if M, I'm just going to write nice enough, stratified space, and there's a whole litany of conditions that you could put here. You could put in the sort of conical conditions that appear in an appendix in one of Jacob's books, but I honestly can't remember which one right now. It's all right, it'll come to me. If it's nice enough, or there's a fibrancy condition that you could require, et cetera, then, well, what am I doing? I'm trying to understand what functors from this exit path category, maybe I should emphasize that there's a poset in the background here, from this exit path category into C should be. And what am I going to tell you? I'm going to tell you that it's exactly the category of constructible sheaves on M relative to the stratification valued in C. If you've never thought of constructible sheaves before, I have good news. The definition is very easy. It's not obvious why it's a good definition, but the definition is easy. The definition is the following. A sheaf is constructible relative to a stratification P if and only if on each of the strata it's a locally constant sheaf. So the idea here is that when you've got a stratified space, you'll have a local system on the yellow bit, a local system on the white bit, and then some sort of gluing information. So maybe there's like something happens that's dramatic between being here and being here, right? You shift down or something. And so this extends this theorem back here. By the way, this theorem is sometimes called the monodromy theorem. And it goes back a long way. Like there are forms of this that Riemann knew, right? And then this is called the, well, I call this the exogamy theorem, because it involves paths that exit rather than just going around. So this theorem is, well, originally it was due to Bob McPherson, and then his student David Truman wrote up a higher category, like a 2-categorical version, and then Jacob Lurie wrote down an infinity categorical version. And there are various refinements and so forth. Okay, so now let's assemble what we've done so far. So I started off by talking about G equivariance, and then I completely dropped the story, right? I stopped talking about G equivariance as soon as I wrote down this category and got excited because I thought this might be a stratified space. And then I saw that it is a stratified space. And now what am I telling you? I'm telling you that G equivariant spaces, I'm going to erase my questions, you can all remember them, right? G equivariant spaces, G spaces, is equivalent to constructible sheaves on, well, a certain space that I'm going to call xg over pg. This is a stratified space, and well, I guess here my sheaves are valued in spaces. Okay, so there you go. And so it really is true that when you pass from the sort of naive equivariance, if we're still using that word, to the genuine equivariance, if we're using that word, then what you're doing is you're really passing from locally constant sheaves to constructible sheaves. That's really what you're doing. So you're taking your space, your BCP, say, and you're adding on stuff, you're compactifying it, and you're compactifying it in such a way that the constructible sheaves that you build are exactly the G spaces, the true G spaces. That is G orb op, yeah. Let's see, I hope not. I was trying to do it right. So let's see, so this here? Well, let's see, so the open stratum is this BCP, right? And the closed stratum is this point. The exit paths go up in this picture. Right, they'll start here and they'll go out. And that's what they'll do. Or they won't, right? Or they'll stay put, but that's okay too. But the point is that they can only go that way.
It's meant to be the nerve of the category. There's only one purpose in going up. There's only an edge rather than a cone.
Well, but if I go up, then I can compose with anything inside BCP. I can compose with any CP. Right. I mean, the nerve of this category is contractible. Right? Yeah. Okay, so I want to try to use that idea. I want to mention something, though. How am I doing? Not that great on time, but let's keep going. So let me mention something about the way this story breaks up the category of G spaces. And this is something that we'll see again once we stabilize, which we're about to do. And again, let me just for concreteness, let me just focus on this story, the case of G equals CP. All right, so we're looking here at CP spaces. And we have two things we can do. One thing we can do is we can take the stalk at the cone point, right, of any sheaf that we might have. So this is, remember, we're thinking of this as constructible sheaves on this cone, and I'm entitled to take the stalk. That's going to give me a space. And let's see, I guess that stalk is a thing I want to call I upper star. I here because I represents closed things, J represents open things. Oh, J represents open things. So that means that if I want to go from C spaces to spaces with a CP action, then I need to, I'll draw it here actually. I need to take a J upper star. So this is restriction to the open stratum. Right, and I have these two things. And well, these functors have adjoints. They have a lot of adjoints, but maybe I'll only draw a couple of them. That's enough for now. I could draw more. Okay, fine, I'll draw more. This is J lower star as well. So this is, I write my adjunctions from top to bottom, left to right. So this is on the far left, right, and this is the Donald Trump wing of things. Okay, and so these things, these functors here, they give you what's called a recollement of this category. What does that mean? That means that I can recover an object here, a CP space, a genuine CP space, from the data of a space with a CP action and a space plus some other piece of information. So what is that other piece of information? Well, let's write it down. So suppose that I'm trying to recover this CP space, and I'm trying to recover it from two pieces of information. Namely, I'm trying to recover it from I upper star of X, and I'm also trying to recover it from J upper star of X. I'm trying to do these two things. Well, what can I do? Well, I can use my unit maps for my adjunction here. And I can mix everything up in the following way. And the theorem is, this is a pullback. So I've recovered X here from the information of I upper star of X and the information of J upper star of X, along with something. Along with what? Well, along with a map from I upper star of X to I upper star, J lower star, J upper star of X. Okay, cool. I can say that a little bit more nicely. I can say that there's an equivalence of categories between CP spaces and the following bits of data. I could have X, which is, I could have X0, sorry, which is a space. I could have X1, which is going to be a space with CP action. Oh dear. I'm just going to write space to the BCP, and we'll see how that goes. And then what's the other piece of information that I want here? Well, I'm going to look at this composite here, the sort of snaky composite here, of I upper star, J lower star of my X1. And so I'll have an additional map, which is sometimes called the art and gluing map, to I upper star, J lower star of X1. And so these three pieces of data recover X, right? Giving me X is the same as giving me these three pieces of data. It's an equivalence of categories. So this is the notion of a recollement. It's an unstable recollement. We'll see that once we get stabilized, we get even nicer structures to play with. But let me put that on the board now. Okay, so I'm halfway through and I haven't stabilized yet. So let's stabilize. So when we stabilize, well, first first let's think about what happens in the non-equivariant case. That seemed to give us some fun things to talk about. So let's try and do the same thing in the non-equivariant case for spectra. And in the non-equivariant case for spectra, we can do the following thing. We can say, well, what kind of category is the infinity category of spectra? And the answer is it satisfies some conditions. So, I don't know, definition, an infinity category is stable if, all right, so let's see what we've got here. Well, I'll give my infinity category a name, I'll call it C. It's stable if there exists a zero object. Okay, so that's an object that's both initial and terminal. 2, there are direct sums. This is sometimes called pre-additivity. You've probably heard that word at least once before, and I'm saying it again. Direct sums means that, well, it has coproducts and it has products, and finite ones, and at least, and they coincide. And notice that the map here really uses step 1 of this procedure, because I need to write down the identity matrix, but I need to know what 0 means, and 0 means go through the 0 object. Just out of curiosity, for what percentage of you is this already familiar? Oh, okay, so like almost everyone. Okay, cool. All right, well then I won't hem and haw too much about this stuff then. So third is the additivity, which says that when you look at the standard commutative monoid structure here, you get a group. And fourth, push-outs and pullbacks are the same thing. Cool. Now then, so orbits are points. Clover promised us that orbits are points, right? And so let's think about how we get from points to this stable infinity category. And well, the answer is the following theorem. The infinity category of spectra is freely generated as a stable infinity category by a single object, which we normally call the sphere. Again, if you wanted to teach a really bad course in algebraic topology, you could give this as the definition. No one would understand, but you could carry on. So orbits are points, so it's got to be the case. So I keep saying gotta be, so you know that I'm about to lie to you. So I might as well write it in red. No, colon. You might want to believe that G spectra, I'll put the G over here, that G spectra are going to be exactly functors from the orbit category, G orbit category, op, into spectra. No, this is false. Maybe I don't like having wrong things on the board. I'll draw a line through. That's not true. It's not true because of the non-presence of transfers on this side of the story, right? We already know that when we take G spectra and we look at the homotopy groups of the various fixed points, that those things have transfer structures, right? They form a nice Mackey functor. And that nice Mackey functor is supposed to come from somewhere, and there's nowhere for it to come from. These things don't have that structure. Now, if you're ambitious, then you might think, well, right, okay, so I just need transfers, so let's just put in transfers, and let's just do it in the simplest way we possibly can. So, what is the simplest way we possibly can? Well, the simplest way we possibly can is what Mona talked about in her lecture a couple hours ago, which is that we want to write down a Burnside category. I'm also going to call this the category of spans. You'll also see this called the category of correspondences. That's what Mike Hill called it. I think those are all the names I know of this thing. And how does it work? Well, suppose that I've got a category C. It could even be an infinity category C. It might as well be. We're already here. And let's suppose that it has pullbacks. Then I'm going to build a new category, and the new category will be called span C, and the objects will be the objects of C. And the maps, well, let's think about what the maps should be here. Well, the maps are going to be spans, because that's what I called the category. So Hom in C from X to Y is one of these. It's a diagram shaped like this. Now, let's remember what Mike and Mona, and I guess Clover also told us about this category. What they told us about this category is that the way you compose these spans is by forming pullbacks, right? You do this by performing pullbacks. Now, we all know that pullbacks aren't unique. They're unique up to a unique isomorphism. We never really worry about that lack of uniqueness, but it is kind of an issue here. And so we're going to take that into account. And this is one of the places where like infinity categories just show up and start doing work for you. Because all I'm going to do, right, is when I give you an infinity category, what am I supposed to do? I'm supposed to give you the n simplices for every n. So I'll just do that. And they look like this. And then I'm going to draw some stuff. x1, 2, ... xn minus 1, n, and it goes on. And at the top here is x0, n, and maybe just to emphasize the point, I will actually include this one. This is x0, 2. Okay, and so you build one of these big roofs, right? It's a big roof. It's a size n roof. And what you require is that these things be pullbacks. That's an infinity category. It just is. This is one of the few examples I know where you write down an infinity category as a simplicial set, and you check the conditions, and you don't use any extra machinery, you just write everything down, but you still get a genuine, non-one category out of this. And by the way, you do get a genuine non-one category, right? If I look at, say, spans of finite sets, then there are non-trivial two morphisms between these one morphisms. So this is the span category, and you want to keep track of those two morphisms. You don't want to do without those. You need those. Those are your friends. Okay. All right, and now I can write down the definition of a Mackey functor in exactly the same way that you've already seen, where the target isn't spectra, but it's something more like the category of abelian groups. But I have this, and I might as well use it. So a Mackey functor on C with values in D, I don't know, something. These are going to be functors from this category of spans into D. And well, let's think about the span category. I have a condition that I need to put here, so I'm not done yet with that definition. But let's think about the span category of C for a second. Well, if C has an initial object, then span C has an initial object too. But like span C is self-dual, right? So that means that if you've got an initial object, it's also a terminal object. In other words, it's a zero object. Ditto for products and coproducts, right? The products and coproducts have to coincide. So what I'm going to say here is that I'm going to try and write down a functor that carries direct sums to direct sums in this sense here. So maybe for this definition, I'll want my D to have direct sums for this to be a good definition. So let's do that. And now what's a spectral Mackey functor of the title? I'll just make D be the category of spectra. That is pretty cheap. Right? I didn't really do a lot of work here. I injected the transfer structure in the sort of easiest way I could from a categorical point of view. In particular, another thing that I want to emphasize here is that I didn't group complete the Hom spaces. There are a lot of situations in which you can take these spaces here, they form E-infinity spaces, and then you can group complete them, and then you'll have like a category enriched in spectra, right? You don't have to do that if your target is already stable. If your target is something like the category of spectra, you're already going into something stable, so group completing isn't going to affect anything. So you might as well live with the concrete thing from my point of view.
We left it as some category D that wasn't stable we would want to.
No, I'm not saying that. I'm saying, what am I saying? I'm saying that this span category, in this situation, for example, this span category will not embed fully faithfully into this category of Mackey functors because of this group completion issue. That's the situation. So it embeds, but it doesn't really embeds. It maps to it, but it doesn't map to it fully faithfully. So that's the real obstruction, insofar as there is one. But this is still a perfectly legitimate definition, even in the case where, like, say if SP was something like connective spectra or something like that, something additive but not stable, it'd still be fine. Or even pre-additive. Okay, so, but what's the theorem? And Mona gave a list of names for this theorem. You may, Dennis Nardin, and then, who else was it? Matthew Nicholas Neumann, MNN, that paper. Anyways, this keeps getting reproved every few, what's that? No, I mean, Dennis really wrote this up. I mean, Dennis is I'm saying that the wrong way. He's the one who really got the setup correct. It's the right way. Now, Dennis deserves credit for this. But what's the theorem going to be? The theorem is going to be that Mackey functors on the category of finite G sets, which does have all pullbacks into spectra, is equivalent to the category of G spectra. And we're using the Bowman convention here for our notation of G spectra. Okay. Questions about this? Yeah. Yeah, so where is this Beck-Chevalley condition in the story here? Well, remember, how does this category look? Well, the objects are objects of C, the morphisms of these spans, so that means that this category contains a copy of C, and it also contains a copy of C op. And those two copies agree on all the isomorphisms. So you've got like a commutative diagram like this. And so if I have a functor out of span C, then that gives me a covariant functor by restricting this way, and a contravariant functor by restricting this way. And now how do the covariant and the contravariant pieces interact? Well, they interact in the following way, namely, when you've got a pullback square of finite G sets, then going this way and then going that way is the same thing as going that way and going this way. Right? Pushing forward and pulling back is the same thing as pulling back and pushing forward. And that's the Beck-Chevalley condition. Sorry, I was not saying the punchline. The punchline is that's the Beck-Chevalley condition. That's what it is. By the way, why does that, you've probably seen like the double coset formula at some point, right? You see in these things, when people define Mackey functors, say in abelian groups, you'll often see them give some sort of double coset formula. Where does that come from? Well, it comes from thinking about orbits. Let's see, G mod K, G mod N, G mod H. Even though that's an N, that's not a normal subgroup. Don't think it is. It's just a subgroup. And you can form the pullback here, and that pullback, if you're taking orbits here, that pullback isn't an orbit, but it's a disjoint union of orbits indexed by the double coset. So you look in G's and, oh Lord, let's see here, N, And then here we're going to do G mod. Oh boy. All right, so let's see here. So G inverse HG intersect K. Yeah, and that's the pullback in this category. Finite G sets. Did I get that right, Natalie? Good. All right. So that's where these double coset formulas in the theory of Mackey functors comes from. It really comes from the formation of pullbacks here. So you see the category of orbits isn't closed under pullbacks, but if you take a pullback of orbits, you get a, a finite coproduct of orbits, and that's really what you need for this story. But that condition, by the way, has a name. It's called being an orbital category. And you don't have to be the category of finite G-sets to be orbital. You can be something interesting, and, or not something interesting, something different and peculiar, and that's a good thing to do too. All right.
What's the condition for it?
It's that the category itself might not be closed under pullbacks, but the coproduct completion, the finite coproduct completion, is closed under pullbacks. And that's a condition that the orbit category of a group has, a finite group, or even of a profinite group. And it's also the condition that's satisfied by some other weird examples, like say, for example, the category of finite sets and surjective maps of cardinality less than n, say, if you want to. An interesting example. Oh dear, okay. All right, well, I better get to some sort of punchline here. So let me now, so now we've got this picture of G spectra as Mackey functors. And let me just sort of briefly show you how to use that picture to get stuff that you have thought about before when you think about G equivariant homotopy theory. And to do this, I want to be very careful with my notation. So I want to go back to this Recollement picture, but I'm going to generalize it a little bit. And here's the way in which I'm going to generalize it. And I would motivate this a little better if I hadn't run out of time drawing my stupid pictures. But I had to draw my stupid pictures. So let's look at another kind of open-closed. Remember, this is the closed half and this is the open half. Let's think about how these open-closed decompositions actually arise. So here's the situation. I'm going to look at a family inside this poset. And let's see, with the yeah, so this is going to be an upwardly closed family with my conventions. Which means this is a family of, if you like, this is a family of subsets of G that's stable under subconjugation. So when equivariant homotopy theorists write a scripty F, this is the scripty F they're talking about. And now what can you do? Well, you can look at the complement of that thing. This is just in this poset here, right? And what I want you to think here, the way I want you to think about this is that these upwardly closed things, remember this poset structure, I'm giving this thing the Alexandrov topology, so upwardly closed is the same thing as being open. And this thing is closed. So what I expect to see here is I expect to see a decomposition like this. All right, well, let's see if we can find it. So we're going to look, when you do these restrictions, right, you can just take your category FG and just look at all the ones where the orbits lie in this family of subgroups. Right, you can just look at that subcategory. So let's look at that subcategory. So we're going to look at Mackey functors on the sort of restricted form of the orbit category, which I guess here on the closed side I want OF tilde. And on the open side, I'm going to have OF itself. And in the middle, I'm going to have G Mackey functors. And now this is going to be another one of these Recollement type situations. If I have a Mackey functor defined on the entire category of finite G sets, I can restrict it to either one of these two pieces. So that's going to give me a functor going, I better do this up more, I upper star and j upper star. And then we have a whole bevy of functors going the other way that decompose this thing like this. And again, in this picture here, this is the closed piece, and this is the open piece. And this is once again a Recollement type situation. Well, okay, if it's a Recollement type situation, then let's try to analyze what these various functors are, these upper stars and lower stars, and let's see that we're recovering something familiar from this gluing diagram. And then I guess that will be the time. So let's do that. That seems like a good place to stop when I'm done. All right, so let's figure out what these functors are. Maybe I'll start on the right-hand side here. So this upper star functor, you know already what that is. It's just a sort of obvious restriction. And this functor in the other direction, well, if you're in traditional notation, this is the thing that's called EF plus smash blank. And then this one, I guess, is therefore going to be the function spectrum from EF plus 2 blank. This is, the people who know this stuff are nodding their heads. That's good. That's always a good sign. And then this one here is what you might call the geometric fixed points for the family F. This is the geometric fixed points for the family F. This I lower star here, this is the one that's usually called EF tilde smash blank. I haven't made any mistakes. Everybody seems happy still. And then this one here, we're not going to use it, but it exists, and it's functions from EF tilde into blank, and then you take F fixed points. So this is how you can translate from this sort of more geometric picture that I was having of spectral Mackey functors into the sort of more traditional functor. And, well, what do you have lying around here? Well, you've got a bunch of sequences, right? This picture here, this Recollement picture, when you pass to the stable setting, it expands to an even larger picture because I can compute the fibers of this map, and the fibers of this map are I lower star, I upper shriek of X, and the fiber of this map is J lower shriek, J upper star of X. And so, well, it's actually the same here, because after all, this is a pullback square. And well, that's a 0. Okay. So in the stable setting, you can expand this picture to this larger picture here. And then you could ask, well, what does this square mean? And maybe, since I only have 2 minutes left, maybe I'll restrict again to the example of BCP, since we're having a good time with that. So let's think about what happens when our category is CP, and we're thinking about the two obvious families in place here. Well, what are the two obvious families? Well, one of them is the closed family, and the other one is the open family, right? There's only one choice that's going to give you anything interesting, so let's take that one. And then, well, what do we have? Well, we have CP spectra. That's on the closed side. Sorry, that's the whole thing. And then on the closed side, what we have is the category of spectra. And on the open side, what we have is, well, just functors. I mean, I could say Mackey functors, but this is a groupoid, so there's not really, transfers are just inverses, so there's nothing really happening there. And you have this decomposition. Right, so we have this decomposition, this Recollement type picture. And then I've got this square, and what is this square telling you? It's telling you that if you want to give me a CP spectrum, then what do you have to give me? And this is exactly a theorem that Jeremy told us a couple days ago. What do you have to give me? Well, let's say that I want to give you those CP fixed points, the genuine CP fixed points of this spectrum. Well, then what do I have to give you? Well, I have to give you the homotopy fixed points. I have to give you the geometric fixed points. Well, let's see, I guess here we're doing this notation, so let's do that. And then I have to give you gluing information, which is given to you by the tape. And what's true is that this is a pullback square, and this square is that square. Minus 1 second. Okay. All right, this is a good time to stop. Thank you very much.
Questions?
So yeah, why is this I lower star, I upper star, J upper star, like this takes B?
Yeah, so let's see that. So, well, let's think about this fiber sequence here, right? So if we think about what this fiber sequence is doing here, well, on this side I've got J lower shriek J upper star of X. So what is that doing? Well, that's taking a naive CP spectrum, right? And it's giving you a genuine one, but how is it doing that? It's giving you a genuine one whose homotopy, whose CP fixed points are the homotopy orbits for CP, right? That's how that functor works. This one does the other thing. It says that the CP fixed point should be exactly the homotopy fixed points, right? So this is really the map from the homotopy orbits to the homotopy fixed points. And well, this is supposed to be the cofiber of that, so it better be the tape spectrum. Yeah?
What about spectral functors?
Yeah, so one thing I did not speak about at all was how the multiplicative structure works. And I didn't even touch that. And the reason I didn't touch that is to sort of start talking about that in this sort of infinity categorical way. The thing you have to do is to shift perspective. And so this is something that Mike Hill told me at a conference in Stanford, I think, in 2013. He said, well, look, you know, you shouldn't be thinking of the category of G spectra as just an infinity category. You should really be thinking of it as a G infinity category. Well, what does that mean? That means that you're looking at a diagram indexed on a diagram of infinity categories indexed on the orbit category of G. And then once you start doing that, that gives you the ability to start talking about things like indexed limits and indexed colimits, and in particular things like indexed tensor products. Right? And it's the, to give you a more precise answer, I'd have to spend some time reconstructing it. But the structure of a spectral of a Tambara functor, at least on the homotopy groups, is given to you by thinking about the tensor product over G sets instead of just over sets. And this is a point of view that Mike Hill emphasized. And oh, that's right. I can make promises for future speakers. He will emphasize this point again tomorrow. I'm just paying it forward.
Can I give a supplement? What do you need of your orbital category before you have Tambara functors defined?
That's a good question. So what do I need of my orbital category? I think I need what's called an atomic orbital category, which I can define for you at a different time. But I think the thing that will make it work is that, I'm going to look to Natalie again to check. Is that right? If I'm trying to get a Tambara functor out?
I think if you wanted to correspond with like G-commutative algebras,
Yeah.
you can use it somewhere. Define it. Define the categories of like spectral Tambara functors without it.
Oh, okay. Oh, but if I wanted to agree.
Yeah, I mean the answer is probably in the formalism elemental non-function hypothesis, this five-span category thing, which doesn't take very many functions to literally find.
Right.
Right, I look forward to.
Yeah, we can.
Are there any more questions?
Should it be enough that pullbacks have a left adjoint in the finally co-product completion to form a Tambara?
In order to have the notion of a Tambara functor? Well, that sounds plausible. At the moment, I don't know, to be honest with you. Can't say.
You said G is finite. Can you say a few words about compactly?
few words about compactly. No, yeah, so what's going on with compactly? So I don't fully know what's going on with compactly. So, yeah, what can I say about compactly? I can't say much about compactly unless G is something like really basic like a torus. And then in the case where G is something really basic like a torus, you can again kind of tell this sort of spectral Mackey functor story, except that then you need some sort of you need some sort of convergence properties for families of subgroups. And I don't know yet how to make that a really precise story. I think it's to me at least, and I'd be excited if someone could answer this question. It's really not clear how to make this story work for G, a Lie group in general. I mean, you know, take SO3 if you're feeling like being concrete. I mean, give me a story like this for G equals SO3, and I think that's a pretty good challenge, actually. Tell me a story. I'll make this an official story, an official challenge. So tell me a story about Mackey functors that recovers G spectra for G equals SO3. I'd like to see that. I don't know how to do that. I would like to do that. I have some thoughts that I can tell you about, but they're not very well refined thoughts. They're pretty scattered, as you might expect. Yeah.
Can you do this whole thing with like incomplete Mackey functors and all this?
Yeah, there's ways to embed further structure here. So yeah, there's various things you can do. So let's say that you don't want to have all transfers, but you just want to have some transfers. Is that the kind of thing you mean?
Exactly.
Yeah. So what you do is you just operate right here in the category of spans, right? And you just redefine that using an auxiliary subcategory of C, which is going to be the subcategory of things that you want to have transfers along. And then you require that your forwards pointing maps lie in that auxiliary subcategory. And then as long as you've chosen the auxiliary subcategory in a good way, then this whole story just falls right out. So it's already here in that sense, yeah. You can even do it the other way where you restrict the kinds of restrictions. I don't know when.
Thank you. I think we've half moved into the question and answer session already.
Sorry.
But I think we should thank Clark again.